Good afternoon, pre-calculus honor students. So this one is just a continuation of the lecture of chapter 3 from pre-cal honors. So you might be wondering the section number is kind of completely off the track. So that's a different textbook I was using before. But for the James Stewart textbook, so this one is supposed to be 3.4, the complex number, and then 3.5, finding the complex zeros. So we'll check out some of the properties of an imaginary number. So I, it's always considered an imaginary number. So I equals negative square root of negative 1. So therefore I square equals negative 1. And also the other property, so a complex number in the standard form is always written as z. So z that involved with the real number a and the imaginary number bi. So a, it's always the real number, re, I am, imaginary number, b. So where a and b, those are the arbitrary constant, which is they all considered the elements of all real number. If you see any symbol like that with the e, capital E like that, that means it's the element of something. So a and b, so those are the elements of all the real number. And z, it's the elements of the complex field, the real number field, the complex number field. Okay, so you see that the unbolded C or the unbolded R, real number, or the real number set, and then this one's the complex number set. So those are just the mathematical symbol things I need to know. So two complex numbers z1, z2 are equal if only of that the real number z1 is the same as the real number z2, and then the imaginary z1 is the same as the imaginary number of z2, which is true. So if z equals a plus bi form, so that means the magnitude or the norm of z, if c the absolute value of z, that means called the norm of the complex number z. So the way to find out that the norm, which means the magnitude, the way to find out the magnitude is about using the Pythagorean Theorem. So let's say we have a plus bi. So here's the y-axis. So here's the real axis. So a plus bi, so the point right here. Well, instead of being the point, it's actually the ray. So started at the 0, 0. So here's a, and here's bi. So the way to find that out is by using the Pythagorean theorem. So a squared plus b squared, and then square root of the whole thing. So to find out the magnitude of z. Okay, so the complex conjugate of z, a plus bi, is z bar. So that equals a minus bi. So z1, z2, so perform the following operations. So basically just combine them. So a plus bi plus the quantity of c plus di. So just regroup them, the real number first. So a plus c. And then the imaginary number. So b plus d quantity times I. So z1 quantity square. So basically this one is just like a plus bi quantity square. So basically, which is what? A squared plus 2abi plus bi squared, or bi quantity square. So we do have a squared. I squared, that's negative 1. So b squared, that's b squared. So negative, negative. So that, well, positive, negative, that turns out to be negative. So a squared minus b squared. And then plus 2abi. The real number, imaginary number. So to prove that z1 times z2, so the magnitude of z1 times z2, or the product of z1 times z2, so that equals the magnitude of z1 times the magnitude of z2. So we want to show both sides are equal. So started with z1 times z2. So let z1 equals a plus bi, and then z2, so z plus di. Okay? So multiply this to complex numbers. So we do have a plus bi times z plus di. And then we'll take the magnitude. Then we want to find out the magnitude of each one of this complex number. Okay, so now let me put it into the new slide for this one, because this one I'm kind of running out of space. Okay, so let me just put it right here. So showing that the product z1 times z2, the magnitude of the product z1 and z2 is the same as the magnitude of z1 times the magnitude of z2. So again, z1, so let's say it's a plus bi, z2, c plus di. So multiply them, so FOIL, a plus bi, c plus di. First, outside, inside, and last. Simply FOIL. So AC plus ADI plus BCI, and then plus BD I square. I square is -1, so it's AC minus BD. You guys see that? I put in all the real number together. Imaginary number, take out that I, and then AD plus BC. Okay, so let's put it right here, one thing at a time. So AC minus BD, the group of this, plus AD minus BC, quantity I. So we'll find the magnitude for this. So now let's find out the magnitude of Z1. Magnitude of Z1, so basically this one is just like using the Pythagorean Theorem. So that one is just like square root of A squared plus B squared. And then Z2, so then that'd be the Pythagorean Theorem with that C squared plus D squared. Okay, so multiply those two radicals, so it's the same radical times, well, it's two different radicals, so just multiply those quantity inside. So it's the radicals of A squared plus B squared times C squared plus D squared. So using the radical property, if we say anything like square root of A times square root of C, square root of AC. Okay, so using the property. And now what about for this one, finding the magnitude? Similar strategy. So this one using the Pythagorean Theorem, the real number, AC minus BD, quantity square, and then plus AD minus BC, quantity square. And then square root of the whole thing. So you might be wondering, would that be under the same structure eventually? Well, let's find out. So this one is just consider A squared C squared minus 2AC BD binomial expansion, and then plus B squared D squared. Okay, so just the left hand side. And then continue with this, another binomial expansion. So this one we got A squared D squared. Okay, so now it's getting a little bit complicated with those letters. But those letters, they're just like real numbers. A squared D squared minus 2AD BC plus B squared C squared, just the left hand side. So you may notice that this one here, so it looks like we can combine them. Check it out. Okay, so the plus. Okay, so this part right here, negative, negative. So it looks like we can combine them. So it's negative 4A, B, C, D. Okay, so what else that we can combine? The rest of this. Well, basically just rewrite it. Okay, so just keep it in this form. Combine them all. A squared, C squared, minus 4A, B, C, D. And then plus B squared, D squared. And then the other side right here, well, this part right here, A squared, D squared, plus B squared, C squared. Just the left hand side. I mean, you can regroup them, you can factor if you want, but just simply keep it that way. And now, what about for the one on the right hand side of this equation? So this one turns out to be square root, again, multiplied it out, so we got A squared, C squared, and then plus a squared times d squared, and then plus b squared c squared, and then plus b squared d squared. Okay, so they're almost identical, but except that minus 4a, b, c, d. Let's see what I did wrong here. Okay, so by the time that I find out, okay, this part right here, z1 times z2, make sure that I did it correctly. Oh, you know what? There's no minuses right in between. It's all plus. Because by the time they multiplied it out, so AC, ADI, BCI, yeah, somehow I put a plus. I don't know why. So this one's supposed to be a plus. Okay, hang on a second. Oh, because that I square. Okay, so check that FOIL once again. AC plus ADI plus BCI. Okay, that's what we found. And then minus BD. Okay, this one's supposed to be minus BD. That's right. Okay, minus BD. And then for the imaginary number, this one is just AD plus BC. Quantity times I. Yeah, this one's supposed to be AD plus BC. Yep, so this one, once you expand it, so this one is negative, but this one is positive, so they got canceled. So there's no minus for A, B, C, D. So check it out. Eventually, they're exactly the same. So A squared, C squared, A squared, C squared, A squared, D squared, A squared, D squared, and then B squared, D squared, and then the last part, B squared, C squared. Okay? So it's under the same radical. Okay, so now let's see what else that we got from this complex number. Okay, so this one is just rationalized in the standard form, so basically multiplied by the conjugate, top and the bottom. So this one, you guys pretty familiar with that in Algebra 2, so multiplied by the conjugate, so 1 minus I. Difference of 2 squared down the bottom, the top part simply FOIL. And then let A plus BI equals M times the quantity of B plus I. Find the value of A and B. Again, distribute. And then compare the numbers. So MB equals A, the real number, equals the real number. Imaginary number equals the imaginary number. So M equals B. So M equals B, so that means B squared equals A. Okay, so find the value of A and B. So just write it in terms of B. So that means M squared equals A. So B equals M, and A equals M squared. So let X equals 1 plus 2I, Y equals 3 minus 3I, Z equals negative 72 be complex numbers. Okay, simplify each expression. So basically just substitution and then simplified it. So Y squared, so 3 minus 3I, quantity squared, plus Z was Z. Square root of negative 72, which is considered 9, well, let's see, 36 and 2, so 6 root 2I. And then this one just distribute, multiply things out, so try to work on it. And then X over Y, Y over X, again, plug in a number, evaluate, simplify it. Things I need to rationalize, then just rationalize it. So the one that I really want to talk about is the I cycle. So we talked about that in Algebra 2 already. So the I cycle, so I is considered square root of negative 1. So I squared is negative 1, so I cubed, which is considered negative I. It's I squared times I, so negative I. I to the 4th power, which is just 1. Because I squared times I squared, negative 1 times negative 1, so 1. I to the power of 5 is just going back to the normal I right here. So I to the power of 21, so it's just like I to the power of 20 times I. Okay. And then plus I to the power of 100, so this one is just I to the power of 5, and then to the power of 20. So I to the power of 20, just like I to the power of 5, I to the power of 4. So I to the 5th power, that's I to the power of 4, it's 1. So 1 times I. So basically this one is just I. And then plus I to the power of 5. We can start with I to the power of 20 first. I to the power of 20, that's just I. To the power of 5. Back to I again. So plus I plus I, 2I. And this one is kind of like a binomial expansion. You want to show the pattern here. So basically, looks like the terms that are going to get canceled out, once you expand it. So start with the first one, so 1 to the 100th power, which is 1. And then you want to drop down the power. So 100 times 1 to the power of 99. And then times negative I to the first power. And then the next term alternating, so minus, and then that's going to be plus. So the next one is going to be like what? Similar to this. And you may notice that on the other side, so basically this one will get canceled. Minus, so we got 1 to the power of 100. Okay, so you see that right here? Got canceled. And then plus. Okay, so negative, negative, so that might be considered what? Well, negative again. So again, it's the same thing. So it's 1 to the power of 100. Well, bring down the power first. It's a binomial expansion. Times 1 to the power of 99 times I. So we see that the negative, positive, 100 terms. So that means the other side right here is going to be it's going to be positive, negative. So most likely, all those terms is going to be canceled eventually. So what's left here? So it looks like the middle term, those are the remaining element. But also they got everything balanced, cancel. Everything got canceled out here. Because that, if the 100 terms, so that, well, if that's 100 power, so the number of terms we have for this polynomial is going to be 101 terms. 101 term. Well, imagine that if that's like x minus y, quantity square, it's like x squared minus 2xy plus y squared. And then the other one is like x plus y. Well, what do you notice? So x squared plus 2xy plus y squared. So once you subtract those terms, so that means the one in the middle, so those are the one that's going to be remain. But the thing is that if that's even power, for the last two terms, so since they're kind of symmetrical, even power, so eventually they're going to cancel out as well. Okay, so once they got canceled out, guess what happened? So nothing is remain. So this one will be considered all zero. Okay, so for number 6, find the absolute value of, okay, so this one, find the absolute value of this form in the standard form. So basically for this part right here, you want to rationalize it first. Once you rationalize it, and then you want to take the magnitude. Okay, so let's find out what that is. So 1 minus I times 1 minus I. Denominator, 1 plus I times 1 minus I, so it's 1 square minus I square, which is what, 2, negative 1, 1 minus negative 1, so 2. So 1 square, which is 1 minus 2i, and then plus I square. And then this one, it's all over 2. So I squared is negative 1, so which is negative 2i over 2. And that would be negative I. So this one, it's like 0 minus I, so taking the magnitude. So what we got, it's what? Square root of 0 squared plus negative 1 quantity squared, so which is what? 1. For what values of p, where p is an integer, is that 1 minus I quantity to the power of 2p plus 2 equals 1 plus I to the power of 2p plus 2. Okay? So this one basically is just like a binomial expansion again. So it's the same power for both sides. If they're both equal, well, it looks like p could be any integer. P is an integer. You can say that positive or negative integer. So we just did the problem like that earlier. Because once you bring everything all together to one side, so just like this one here, so basically they got everything cancel. You take this one back to the left hand side if they're equal. So it got to be the exact same power. Okay, so p could be any integer except 0. And then for number 7, excuse me. So z equals 1 over the quantity of 1 plus 3i. W equals I over the quantity of 1 minus 2i. So az plus bw equals 2. Find the value of a and b. So again, similar to what we did. So az plus bw simply multiply them. Set that equals 2. So kind of like solving the rational expression. So convert that to the same denominator and then put this all together and try to rationalize it eventually. Okay? So try to find out the value of a and b for this one. So convert that to the same denominator. So we got 1 plus 3i, 1 minus 2i. And then this part is like a times the quantity of 1 minus 2i. And for this one is like bi times the quantity of 1 plus 3i. So eventually that's going to be 2. Okay, so this one multiplied it out, rationalized the top part, distribute, combine the like term. So once you simplify the whole thing, and then you just solve for the value of a and b. Okay. So for 2.5, the real and the complex zeros. Find the real and the complex zeros. So this one basically simply just factor it. So take out x to the third power. So we got x to the fourth plus x squared minus 20. And then the rest of this, well, we got 0. That appeared 3 consecutive times. Multiplicity. 3 times. And then the rest of this trinomial, so it's an even power. Simply using the factor tree, x squared, negative 20. So 5 and negative 4. So we got x cubed, x squared plus 5, x squared minus 4. So try to factor it out, or just set it equal to 0. So x equals 0, we find it out already. So 3 times, all 0. Well, x equals 0, not x equals 3. And then this one, that would be what? X equals plus minus root 5i. And then over here, x equals plus minus 2. Difference of 2 squared. So we got 3 real zeros and then 2 imaginary zeros. And then for 2a, 2b, it's about using dot p over q. Okay, so I'll do 2b there, because that one looks a little bit more complex. So once you reduce down by using the synthetic division, so the rest of the 0, you can simply either factor it, or you can use the quadratic formula. Okay, so for number 2, again, similar to what we've been doing in Algebra 2. Okay, so what we got here, so started with that p over q, the rational zero theorem. So again, p is all the possible factors of the constant term, negative 2. So negative 2, we got negative plus minus 1 plus minus 2. And then q, that would be the possible factor of the leading coefficient, which is what? Plus minus 1 plus minus 2 plus minus 4. Excuse me, something wrong with this. Okay, so plus minus 1, plus minus 2, plus minus 4, plus minus 8. Again, all the possible factors of 8. So according to the list here, we got plus minus 1, plus minus 2, plus minus 1 half, plus minus 1 fourth, plus minus 1 eighth. So are we going to test all of them? Well, depends on whether you're lucky or not. So bring down the coefficient. We got 8, negative 4, negative 18, negative 11, negative 2. And you may notice that the majority of the number, they're all divisible by 2. Okay, so let's start with 2 first. So 8, bring it down. 8 times 2, 16, plus negative 4, then that'll be 12. 12 times 2, 24, plus negative 18, 6. 6 times 2, 12, plus negative 11, 1. 1 times 2, 2. Bingo. It works. So let's keep going. So this one we just reduce down to the cubic power. Because once you rewrite it, it's like ax cubed, 12x squared, 6x, and then plus 1. But the thing is that we're doing it without the variables and the power. So that's the beauty about the synthetic division. Unlike the long division, you have to come up with the power, degree, the variable, remainder, all that. So another number I want to try, since 2 that works, so what we can do, the reciprocals of 2, or perhaps the opposite of that number. Let's try negative 1 half. Okay, so 8, bring it down first. 8 times negative 1 half, negative 4. 12 plus negative 4, which is what? 8 again. 8 times negative 1 half, negative 4, plus 6, 2. 2 times negative 1 half, negative 1, 0. Bingo. So what we found here, we got x minus 2, x plus 1 half for those factors. And now the rest of the factor here, we got what? 8x squared plus 8x plus 2. And looks like this one, is this factorable? Let's find out. So we got 8, 8, and 2. So basically we can take out 2 first. So we got 4x squared plus 4x plus 1. So this one, obviously, we need to try what? 2x plus 1. And then 2x plus 1. It's a perfect square trinomial. So 2x times 2x, 4x squared, 2x plus 2x, 4x. Okay, so it looks like we do have x equals 2, one of the real 0, x equals negative 1 half, the one that we did with the synthetic division. And also this one would be the multiplicity. So on the graph, then that would be horizontal tangent, on the x-axis. So x equals negative, well, this one, that appears 3 consecutive times then. So we can keep using that negative 1 half. Okay, so let's try that one more time, negative 1 half. Does that work? 8 times negative 1 half, negative 4, plus 8, 4 times negative 1 half, negative 2. It does. If you keep trying it, it will work. 8, bring it down. 8 times negative 1 half, negative 4, 0. So 2, and then negative 1 half. So that would be the multiplicity. So that appears 3 consecutive times. So make sure that this way you need to say that x equals negative 1 half. Multiplicity. Three times. Okay, so now let's see what else. Okay, so write the polynomial with degree 4 with the leading coefficients. So this one, we do know f of 1 equals 2. So basically this one, you just put in that x plus 2. And also we need to apply the conjugate theorem. So x minus root 2i, that's one of the roots. So that means x plus root 2i, that would be the other root. The other factor, which is what? Negative root 2i. The conjugate is also part of the 0. Negative 1, so x plus 1. And then the leading coefficient, we don't know what that is, so it's a. But we do know that the function is going to be, well, when x equals 1, so it's going to be 2. So once you plug in 1 for x, and then you can solve for a. Okay, so solve for a by plugging a number, x equals 1, y equals 2. Okay, so try that one. So it's 1 plus I, a zeros of x cubed plus 2x squared minus 6x plus 8. Justify your answer and factor completely if possible. So try to use that p over q first. So just find out all the 0. So if this one is one of the 0, so that means it is. Well, if that's something else, then obviously it's not. So using that P over Q to find out all the zero here. The rational. And then once you get a rational, then you'll be reducing down to quadratic for this polynomial. And then from there, find a complex root. So find the zero of the polynomial. So basically set equal to 0. Okay, so this one looks like we can factor it. Can we factor it? No, we can't. So expand it out, and then using that P over Q again. State the end behavior. So take out that the power, x to the 4 power. The function of g of x equals f of 2x minus 2. Well, this one, what does that involve? The value b, you can put out that first. So it looks like the phase shift, then that would be considered 1 unit to the right. So putting into the function, then that would be 2 times x minus 1, and this whole quantity square, plus 2 times x minus 1, minus 16, and then this whole quantity square, and then minus 16, for the transformation of g of x. Okay, so a lot of those stuff, they're kind of similar to what we were doing in Algebra 2. So check out that things that we did in Algebra 2, which is going back to, what chapter was that? That was back to the polynomial, which is chapter 4. Complex number, finding the complex zeros, things like that. And then the third part of the lesson for pre-cal honors, so this one is about going back to rational functions. And also rational function, we talk about that in Algebra 2. And that was going back to, that was what, chapter 7, rational functions. Okay, so we'll take a look at those for the third part of the video. The way to find the asymptote, VA, HA, and the slant asymptotes. And then the way to sketch the graph with 3 different scenarios. Degree on the top, greater than the degree down the bottom, or the degree is the same top and the bottom, or the degree on the top is less than the degree down the bottom with the rational function. Okay, so we'll take a look at that for the third part of the video. So again, any questions that you have, so you guys are more than welcome to put up the comments, questions, things like that on the YouTube channel. So thank you for watching the video today. So I'll see you guys next time. You guys have a great one.